Thank you very much. It's a pleasure being here with you to share the Enoda story. And for me, that story started more than 2 decades ago when I was the first energy security advisor to the NATO commander. And I left my time at NATO with 2 understandings. Number one, the only solution for long-term allied energy security was a system based on renewable energy. Not because I was trying to save the planet, it's an admirable goal, but it wasn't what I was doing then, but because renewables are the only technology that allows you to produce ample domestic energy where the price of that energy and your economy as a result are not hostage to global geopolitics. But on the other hand, the electricity grid that Nikola Tesla, William Stanley, and George Westinghouse built for us wasn't designed to work that way. It required these big thermal spinning power stations that can create the AC waveform we all share and dynamically stabilize the grid by adjusting their output to match the demand we have at this instant for energy to keep the frequency stable at 50 hertz. They do that so well that we forgot they did that. We thought they only generated primary power, and so we got rid of them to generate primary power with renewables, and we created a whole bunch of problems as a result. So today, we have trouble balancing the local network. We have trouble adapting the local network to support electrification. I know there are some heat pump people here, and you have horrible experiences trying to install heat pumps because the network isn't meant to do that. We don't have a clean electricity signal, and so we have real constraints on digital load growth and the information economy. We don't have a secure way of managing these systems. So for my entire career, we've had the promise that we'll have smart refrigerators balancing the grid, and that's too complicated to deliver today, just like it was too complicated to deliver in 2005. And critically, we don't have a source of affordable decarbonized frequency services. So when the sun passes behind a cloud or the wind picks up, we don't have a way of adjusting our consumption of energy to keep the system balanced. So this is from an academic paper by our chief economist, Professor Ryan Williams, that correlates, given current technology, the cost of delivering energy with the share of renewables in the system. And what we see is that at about the point we are today, roughly 45% penetration, the cost of stabilizing the grid begins to rise exponentially because we've taken out those spinning power stations that provided both frequency services and stability, as well as primary power. So we need a new source of system stability, which is what we're delivering at Enoda. This is a 400 kVA prime exchanger. It replaces the distribution substation, the secondary substation at the end of your road. So it supports, say, 120 homes with single-phase power, or a building the size of this one. Maybe this block, this building isn't that big, but a building that's roughly the size of this block with single-phase power, and it transforms voltage like a transformer does, but it also dynamically manages the electricity signal. So that means that we can correct all of the instability introduced by the energy transition, and we can adjust the voltage, which adjusts the load. I'll explain that in more detail, to ensure that we keep the frequency stable. So how do we do that? We do that through something called dynamic modulation of flux through near-field induction. I wasn't planning to talk about this, but Julia wanted me to explain it. So here on the left-hand side, you have an input signal, say coming from the low voltage network from a group of homes. And on one of those phases is a nasty fifth harmonic that might have been created, for example, by a cheap inverter on a rooftop solar array. If that harmonic propagates up the network, the carrying capacity of those poles and wires will be reduced by up to 30%. And today we don't have a good way to fix it. We impose a second electromagnetic signal at a much higher frequency inside the core of that device. We recover the energy that's currently being lost in that harmonic and produce a clean output signal that matches what the Tesla Westinghouse AC grid was designed to take in the first place. So that lets us control the voltage of the network, correct the electricity signal, but we need to do that at scale to enable the transition. So how do we do that? So in a traditional, this is a typical distribution network. This one happens to be in Poland, so it looks a little bit different to the UK. In a typical transformer-based substation, the assumption is that the voltage is simply transformed and then it cascades down. But in this example, on a sunny afternoon, we have these residential homes and this small DER, group of DERs, which are reverse power flowing and providing power back to the network. And as a result, the voltage is approaching and possibly exceeding the regulatory boundary. So the DNO, or the DSO in Poland, will say, I'm not going to permit any more solar on that feeder because I don't want to violate my voltage boundaries, or as is the case in a lot of feeders like this, we might have regular brownouts or occasional blackouts because the voltage violates the regulatory boundary. We go in and look at that, and our device, the prime exchanger, sees that it has this excess voltage at the bottom of the network. Excess power reduces the voltage of the entire feeder to bring it back into specification. So we see the difference with the transformer-based substation. And then we've now, not only are these DERs able to continue to produce energy and inject it up in the system, but we've unlocked that network to support additional DERs, and we can do the same thing in the opposite direction for example, heat pumps in the evening or electric vehicle charging. Now, what's particularly exciting about this is, in order to do this, we only had to reduce the voltage by 5%. And that means that all of the loads are consuming slightly less power. So hands up if you realize that your kettle boils at a rate that varies in a 20% error bound. There must be someone who's, anyway, it does, right? The voltage, but you don't notice that your kettle sometimes uses slightly less power and sometimes slightly more. If we take advantage of that random variation across the system, we can replace the needs of a power station like Drax, because when solar production falls, instead of reducing this by 5%, we reduce it by 10%, and we bring the system back in balance. Everyone's kettle boils slightly slower, no one notices, but we end up consuming slightly less power, and so we don't need that spinning power station to balance the grid. We're currently in pilot deployments in 2 countries, Poland. Why Poland? For obvious reasons. Poland's had a 20-year commitment to energy security, and every time a Russian missile hits a Ukrainian substation, that literally propagates across the grid into Poland. So Poland today has the fastest growth of renewable energy in Europe, the most negative prices as a result in Europe, and knows that in order for renewables to deliver on energy security as well as decarbonization, you need a at-scale solution for system stability. The second example, before the blackout, we began this project in Spain. So Spain is in a similar sort of situation to Poland. Tremendous adoption of renewables very quickly, but very little investment for a variety of reasons, mostly focused on affordability in what I would consider kind of band-aid technologies like batteries, synchronous condensers, et cetera. That meant that in the blackout, Spain didn't have the resources to respond to a frequency event that led to voltage oscillation and so forth, and eventually the blackout. But Poland and Spain are both in a really exciting position in the sense that they have large fleets of renewables and the opportunity to leapfrog directly to the next generation of technology, which is this, our edge-to-cloud platform. So at a hardware level, the prime exchanger, that manages the network locally, but then is able to send that data up into an integrated digital twin in the cloud that lets us understand across the entire network what is the available flexibility in order to manage the network, how much flexibility can we offer to balance the grid, where are the problems emerging that need to be addressed, et cetera. So we're turning what is today the world's largest machine, and happens to be the world's largest analog machine, into the world's largest, most intelligent autonomous system. I wanted to end just by sharing a couple of thoughts as a founder. So when we started on this journey, we thought that we were going to be an asset-light IP business, developing innovative designs and monetizing them through an established collection of OEMs who would manufacture our equipment. And that didn't work. And it didn't work because the future is further from the present than we thought. We needed not just to invent the designs, we actually needed to invent a whole range of new materials, a whole range of new manufacturing technologies in order to be able to bring the future here to the present. We thought that we were sitting in, like ARM, with an established collection of fabs that could make a new design, and really we found out that we were more like Silicon Valley in the 1960s, needing to figure out how to make microchips at scale. So I'd leave you with the thought that we're delivering the technologies to deliver the transition, but we really need to think about how are we going to scale those technologies into the opportunity and into the requirement that we face. Thank you very much.